Hi friends, here in this video I'll be explaining a problem on critical speed of shaft. So let's get started. Now here is the question. It is given a vertical shaft of 20 mm diameter. Now whatever is given in this question, I'll write that in the form of data first. So here is the data. The shaft is having a diameter of 20 mm. So when the diameter is given, I'll find the area of shaft, which is the cross-sectional area, and it comes out to be 314.16 mm square. Next it is given and 600 mm long. This is the length of the shaft given, denoted by small l, is held in short bearings. So it is mentioned that the shaft is held between short bearings. This we have to write in the data that this is the type of bearing. So I'll write down that the type is short bearings. Next, a 5 kg disc is mounted on the shaft midway between the bearings. Mass of the disc is given. So when the mass is given, I'll find the weight of the disc, and that will be W is equal to M into G. M is 5 and G is 9.81. So the weight of the disc is 49.05 Newton. Then between the bearings, CG of the disc is 0.5 mm away from the axis of the shaft. So this distance which is given, it is the eccentricity, denoted by small e, 0.5 mm, and that is 0.5 into 10 raised to minus 3 meter. Next, if the allowable tensile stress for the shaft is 70 Newton per mm square, so the allowable tensile stress, this tensile stress can also be considered as the bending stress, 70 Newton per mm square, because when any object it is bending, in that there is tension as well. So the tensile stress is taken as sigma b, which is the bending stress. Next, determine the critical speed of the shaft. So we have to find what is the critical speed of the shaft, denoted by n suffix c. I'll find the speed in terms of rpm. Nothing is mentioned in the question, so we'll find it in terms of rpm. Next, the range of speed which is not safe. So we have to find out the speed range. Speed range in which the shaft should not be operated means it is the not safe range of speed, because in that speed range the shaft may break. And take E, that is the Young's modulus 200 GPa, denoted by capital E. Since it is 200 GPa, that comes out to be 200 into 10 raised to 3 Newton per millimeter square. So this is the question in front of us. Now let us get started with the solution part. Now in the solution part, since it is mentioned that it is a short bearing, so I'll write down, since short bearings are considered as simply supported beam, and here it is mentioned in the question that the rotor or the disc is exactly at the center, it is in the midway of the shaft length. So the short bearings are considered as simply supported beam. So I'll draw the diagram of a simply supported beam. The load is at the center, and this load is corresponding to the weight of the disc. Exactly in the midway. Since the length of shaft is 600 mm, So the weight is acting at the midway, so it gets divided into two equal halves. Now, for simply supported beam, under the action of load, it will deflect, and this is the deflection of a simply supported beam. In other words, that is the static deflection of the shaft. So here what we are going to do, we are going to find the static deflection of the shaft first. Static deflection will be due to the weight which is kept on the shaft. Means right now the shaft is not started, just under the action of load it is going to deflect. So I'll write down that for a simply supported beam which is supported at its ends, the static deflection is given by denoted by delta, and that is WL cube upon 48 EI. So this is the formula we have to remember for static deflection in case of a simply supported beam where the load is kept at the center. If the load is away from the center, then this formula would change. So here it is WL cube upon 48 EI, and I am keeping this as equation first. Now here is the axis of the shaft. The point which is coincident with the center of the disc is denoted as O. O is the point which is there on this axis. Similarly, S is the geometric center. Here I'll mention S is the center of the disc. In this case, both the axis of the shaft and the center of the disc are coinciding. Next, the eccentricity is given because in the question it is mentioned that the CG is away. So here this point which I am indicating, that is G, which is the CG of the disc where the entire mass or the weight of the disc is accumulated, and this distance is given to us. That is nothing but the eccentricity with respect to the geometric center of the disc. So it is eccentricity E, and from here there would be a centrifugal force which would be acting when the shaft is getting rotated. So in the first case which I am considering now, here the shaft is in the static condition as shown in figure, and this same figure in which there is a shaft supported between two bearings, I'll name them. Here is bearing A and this is bearing B. So the shaft is supported, and this is considered as a simply supported beam which I have shown here. So the arrangement which is shown in the vertical form here I have shown it horizontally in the form of a simply supported beam. So under the action of this load of this disc, the beam is going to get deflected. So the beam is deflected, in other words this shaft is going to deflect, which is called as the static deflection when the shaft has not started to rotate. So therefore weight is known to us, Young's modulus, that is also given in the problem. So I is the mi, so I'll write down therefore mi, that is the moment of inertia of the disc. Since the disc is circular in section, so therefore the moment of inertia formula is pi by 64 d raised to 4. Therefore I will be equal to pi by 64, the diameter is 20 raised to 4. So therefore I value will come out to be, it is 7.85 into 10 raised to 3 mm raised to 4. So this is the mi of the disc. Next I'll put all values in equation 1 and get the static deflection. So putting all values in equation 1, hence static deflection will be equal to W, it is WL cube, W value is 49.05 into L cube. Now L value I would be putting it in terms of mm since it is given. It is 600 mm upon 48 EI. E value is 200 into 10 raised to 3 Newton per mm square, and moment of inertia I is 7.85 into 10 raised to 3. So after calculation, I'll get the static deflection value, and it comes out to be, it is 0.14 mm. And this static deflection, I am writing it in terms of meter as well, because that would be required in order to find the critical speed of the shaft. 0.14 into 10 raised to minus 3 meter. Now once the static deflection is known, I can find the critical speed of shaft, and it is given by the formula. The critical speed of shaft is omega c, and that is equal to the natural frequency of the system. Why it is equal to the natural frequency of the system? Because critical speed is that speed at which the shaft will start rotating violently. Violently means the amplitude of vibration would be very huge, or we can say it will try to approach towards infinity. So that is the critical speed at which the amplitude of vibration is maximum. So that critical speed will be maximum when it is equal to the natural frequency of shaft. So therefore, or we can say the natural frequency of the disk. So this critical speed would be given by the formula of natural frequency, which is root of k by m, and therefore k is the stiffness. We can say that k is the stiffness of the shaft. So therefore stiffness is given by load, which is weight, upon deflection, and here it is static deflection, upon we have mass, and that is in terms of equal to weight is given by m into g. Similarly in the denominator we have delta into m, that is mass. So mass will get cancelled out from the numerator and the denominator. What remains is critical speed is equal to root of g upon delta. So this is the formula for critical speed. Now I'll put the values here. So therefore the critical speed is equal to root of g is 9.81, and static deflection, since the unit of omega c would be in terms of radian per second, we have to keep the deflection in terms of meter. Then only we are going to get the angular speed. This is the angular speed in terms of radian per second. So deflection is 0.14 into 10 raised to minus 3 meter, and that will give us the angular velocity or angular speed of rotation of shaft, which is the critical speed. So therefore the critical speed, when we calculate it, it comes out to be 264.71 radian per second. So that is the critical speed, or we can say the angular velocity or the angular speed of shaft, which is the critical speed. And therefore now to convert it into RPM, since omega c is also equal to 2 pi nc, now this will give me the speed in terms of revolutions per second, that is RPS. So first I'll say that therefore nc will be equal to 264.71 divided by 2 pi, and it is 42.13 revolutions per second. Now therefore once we have revolution per second, we can multiply it with 60 to get the speed in terms of RPM. So when I multiply it, I'll get the critical speed in terms of RPM, and my answer is 2527, that is 2527.8 RPM. So that's the first answer. It means this is the critical speed, and the shaft should not be operated at this speed, because at this speed the amplitude of vibration will be maximum and the shaft will ultimately break. So this is the speed at which it should not be operated. Now we have to find the range of speed which is unsafe for the shaft, and for that we have to consider the dynamic condition. And for dynamic condition, here I am considering the rotation of the shaft, and this is omega. From this CG there will be a centrifugal force which would be generated, denoted by M into E into omega square, centrifugal force acting away from the center. Now we have seen that due to the weight there is static deflection, and due to the centrifugal force when the shaft is rotating there will be another deflection which is called as the deflection due to the dynamic load, and because of that the shaft would be rotating in a curvature form. It will try to rotate in this manner. Here I am indicating it, that the shaft would be rotating violently somehow in this condition, that is it would bend and then try to rotate. So we are going to get more amount of deflection, and so I'll say that therefore the deflection due to the dynamic load will be given by, after getting the critical speed of the shaft, deflection due to the dynamic load, and that deflection will be denoted by small y, and the formula is, now it is W suffix d, where W suffix d is the dynamic load considering the rotation of the shaft, L cube upon 48 EI. I am keeping this as equation second. The formula is similar to the static deflection, but we have to remember, in case of static deflection we have taken the load of the disc, but here we have the dynamic load, and in order to calculate the dynamic load we have to use the concept of bending stress. So therefore I'll say that bending stress, because the shaft is bending while rotating, is given by sigma suffix b is equal to m upon z, where m is the maximum bending moment and z is called as a section modulus. So therefore sigma b will remain as it is. Instead of m I'll put the value m in case of, that is the maximum bending moment for a simply supported beam, since we are considering short bearings as simply supported beam with point load at the center. So for such a condition the maximum bending moment capital M is given by W suffix d, the dynamic load, into L divided, which is the length of the bearing, divided by 4. So this is the maximum bending moment. Next, Z is the section modulus, and therefore since the shaft is circular in section, for a circular section the section modulus is given by, it is pi by 32 d cube. And how this formula comes from, we can say that the section modulus Z is given by I upon y. I for a circular shaft is pi by 64 d raised to 4, divided by y is considered as the distance from the neutral axis to the topmost or the bottommost layer. I'll draw the section here. This is the section of the shaft having diameter d. Here is the neutral axis. So the distance from the neutral axis to the topmost fiber or to the bottommost fiber is denoted as y. So y in this case is the radius, which is d by 2, the cross section of the shaft. So it is pi by 64 d raised to 4 into 2 upon d, because this will become reciprocal when I convert division sign into multiplication. So after this, after the cancellation, we are left with the formula Z is equal to pi by 32 d cube, and the unit would be in terms of mm cube. So that's how the formula of Z comes from. And then for M, it is WL by 4. That also we can derive for a simply supported beam. And that formula of M can be said in this way. Like for example, I'm just explaining it quickly, that since the load is acting at the center, so at both the ends it would be W by 2 and W by 2. That is, the load gets equally distributed. So when I take the moment at the exact center, that would be W by 2 into this distance is half. It means it is L by 2. So when I take the moment at the center, which will give me the maximum bending moment, so that would be WL by 4. So that is how the formula of capital M comes from. Now, once we know these conditions, here we have cancellation. So therefore, sigma B will be 8 WD, that is the dynamic load, into the length between the bearings divided by pi d cube. Now in the problem, the bending stress is given, the tensile and bending stress, they are same. So therefore, sigma B is given as 70. WD is the dynamic load, L the length between the bearings 600 mm, the diameter of the shaft is 20 mm. So therefore, the dynamic load will come out to be, and it is 366.52 Newton. Now once the dynamic load is known to us, we can put all values in equation second and get the value of Y, which is the deflection due to dynamic load. So therefore, putting all values in equation second, hence Y is equal to WD, which is the dynamic load, 366.52 into L cube 600 mm, 48, E is 200 into 10 raised to 3, I, which is the moment of inertia of the section, 7.85 into 10 raised to 3. Now on calculating this, the answer of Y comes out to be 1.05 mm. I'll even convert it in terms of meter because that would be required in the further part of the solution. So in terms of meter. Now once we know the deflection due to the dynamic load, we have to consider both the positive and negative values for this deflection in order to calculate the speed range, and that is given by the deflection due to dynamic load is given by the formula Y is equal to, it is omega upon omega c whole square into E divided by 1 minus omega by omega c the whole square. So that is the formula, and we have to consider both positive and negative values in order to get two different speeds. Now this formula is in terms of omega, which is the angular velocity. The same formula can be written in terms of the rotation, which is RPM, in terms of revolutions per minute. So what I'll do here is, the same formula I'm going to write it in this way, that it is plus or minus Y is equal to N upon NC whole square into E upon 1 minus N upon NC the whole square. So this is the formula of the dynamic deflection, and in this we have to place the value of Y in terms of meter, and even this E would be in terms of meter. So I'm going to put the values and we are going to get the speeds here. So first we are taking the positive value, so I'm writing here that we have to take both values one by one. So first, considering the positive deflection, that is plus Y, which is 1.05 into 10 raised to minus 3 meter. Now therefore, by taking this value, eccentricity is given in the problem. It is 0.5 mm divided by 1 minus n upon nc square. So therefore what we can see from both sides is 10 raised to minus 3 and 10 raised to minus 3 getting cancelled out. It means even if we put the deflection in terms of mm, we can get the answer, but the thing is we have to take both the units as same. Example, the unit of y and e should be same. So now it is in terms of meter. If they are in mm, then also the answer would be correct. So therefore I'll simplify it. Here we have 1.05 left. This entire term would be multiplied to the left hand side. 1 minus n upon nc the whole square and equal to 0.5 n upon nc square. So therefore, now for the simplification part, here 1.05 gets multiplied inside. So we have 1.05 n upon nc square. I'll keep the similar terms on one side. So minus 1.05 n upon nc the whole square, when shifted to the right side, it gets added in 0.5. So on one side I have the value 1.05, on other side 1.05 when gets added with 0.5, it comes out to be 1.55. Next, here 1.55 would be in the denominator of 1.05 and we want n upon nc. So this square would be shifted on the other side, that becomes root and it is equal to n upon nc. Therefore the answer is n upon nc is equal to 0.823. Now we are going to find the speed, which is by taking the positive deflection. So here I am denoting this speed as n1. nc is already there with us, so n1 would be 0.823 multiplied by the critical speed in terms of rpm, and nc value was 2527.8. so when these get multiplied, I am getting the value of n1 and my answer is 2080.38 rpm. So that's the first speed. So after getting n1, the second answer, now in a similar manner I am going to consider the negative value of y. So considering y value as negative, and we have seen that if we put it even in terms of meter mm, then also it would be fine. So I am just writing it first in terms of mm. So therefore here I am going to get 1.05 on one side, on the other side it is n upon nc the whole square, and we have 0.5 which is e value divided by 1 minus n by nc the whole square. So therefore again this term would be shifted on one side, and when after the simplification, so that will become 1.05 plus 1.05 n by nc the whole square is equal to 0.5 n by nc square. Now this 1.05 term, when goes on to the other side, we have 0.5 minus 1.05, and that gives me the value as, on one side we have minus 1.05, on the other side that would be minus 0.55 n upon nc the whole square. Negative sign from both the sides will get cancelled out. So therefore the ratio of n upon nc will be, in a similar manner we can calculate it, 1.382. and now since we are going to find the second speed, I am denoting it as N2. So therefore N2 will be equal to 1.32382 multiplied by the critical speed, which is 2527.8 rpm. So N2 value comes out to be 3493.42 rpm. Now that's the third answer. Then whatever the speeds which we are getting, I'll explain it onto a diagram. That is the final answer. I'm going to represent it with the help of a diagram. So here this graph is indicating bending stress on y-axis, on the vertical axis, shaft speed on x-axis. So I am taking the bending stress value as 70 Newton per mm square, which is given in the problem. Next I am taking it as 80, and then it is 90, and finally 100 Newton per mm square. Then the critical speed of shaft would be exactly at the center, we can say, where we are going to get the maximum deflection. So here is the critical speed, which is NC 2527.8 rpm. So this is the critical speed, and as we can see at the critical speed, the bending stress is also pointing towards infinity. Similarly, the deflection of the shaft will also be towards infinity, and N1 speed at 70 we have to see. So this point on the graph would show me the speed as N1, which was 2080.38, and that is in terms of rpm. So this is the N1 speed. Next, N2 speed is there at this intersection, that is of 70 Newton per mm square stress given in the problem, and this curve. So here I am getting the speed, which is N2 3493.42 rpm. Now what is the meaning of this graph is that the shaft should be operated at a speed of 2080.38 rpm and below, because here the graph is dropping. We can see the stress is 70 up to this limit where the speed is 2080.38 rpm, but the moment we increase the speed, then the stress would go on increasing, and the permissible stress is only up to 70. So the stress should not cross this value. It means we have a limiting speed of 2080.38 rpm, and anywhere in this region just below this speed we can operate the shaft, because that will give us the less value of stress. As we can see here, the stress is dropping with the speed, so the safe values would be up to 2080.38 rpm. Similarly, when we see the other side, in that case, if we are operating the shaft at a speed of N2, which is 3493.42 rpm, that is the limiting value, and if we go on increasing the value of speed beyond this value, like for example if it is 3700 rpm, then obviously that speed would be towards right hand side and the stress value will drop. So when the stress is less than 70 Newton per mm square, that is the safe value of speed. But if we operate at a speed which is less than 3493, then that speed would go onto the left hand side, and we are going to come in that region in which the stress value will be more than 70. So that will result in the breaking of shaft, and here is the critical shaft speed of shaft, which is 2527.8 rpm. It means try to avoid operating the shaft in this range, or we can say avoid the shaft approaching the critical speed. We have to keep the speed either less than critical value, or we have to keep it greater than the capital value, but we cannot operate the shaft in this zone which I am showing here with the help of shaded area. No need to operate the shaft in this region. So this is the unsafe zone. The shaft cannot be operated in this region because there only we are having one value which is critical, that is 2527.8 rpm. It means when the shaft will reach this value, it will try to get maximum amplitude of vibration and may finally break. So to avoid it, we can operate the shaft anywhere below the speed of N1, that is up to 2080.38 rpm and below would be fine. Similarly, at a speed of 3493.42 rpm or greater would be applicable for this shaft. Means we cannot operate in this region. So this is the next answer, because we have to find out the speed range which is not safe. So we can say that the speed range anywhere between 2080.38 rpm to 3493.42 rpm is the unsafe zone. The shaft cannot be operated in this region. Anywhere below 2080 and greater than 3493 rpm would be fine. It means the shaft will not fail under these rpm or these conditions. So these are the speed range in which the shaft should be operated: greater than N2 or up to N2, that is minimum speed N2 or greater than that, or maximum speed of N1 or less than that. Not in this region, because that may ultimately lead to the critical speed where we are getting maximum bending stress, maximum deflection, huge amount of amplitude of vibration, and finally the breaking of shaft. So in short, that was a problem regarding the critical speed of shaft. At the end, if you all find my videos helpful, you all can like, share, comment and subscribe our channel and share it amongst your family and friends. Thanks for watching.